So thermal expansivity is the expansion or change in dimension of a body on the application of heat. Okay, this change can be length, density, area, or volume. So when we heat bodies up, it's expected that most times there's going to be change in their physical properties. Alright, so thermal expansivity is trying to explore those changes. Alright, first of all, the expansivities we'll be considering is linear expansivity. Now, this is a change in length of an object due to heat. So it's more like you applied heat on an object and you want to consider the change in its length. Okay, so different materials expand through different lengths when heated over same range of temperatures. Okay, this is represented by the linear expansivity of the material. Okay, so linear expansivity is the increase in length per unit length per degree rise in temperature, and the unit for linear expansivity is per degrees Celsius or per Kelvin, and can be mathematically represented by this. Okay, so this is increase in length per unit length per degree rise in temperature. Right, the same here, increase in length, that's change in length per unit length per degree rise in temperature. So that's what this formula is about. So we have our L1 to be the initial length of the substance. That's the length the substance had or the object had before heat energy was applied to it. L2 is the final length after heat energy has been applied. Temperature 1 is the initial temperature before the apply of heat energy, and theta 2 is the final temperature after heat energy has been applied. So it's very important to note these formulas. We'll use them to solve questions when we get to solving exercises. Next, we can see that every substance has its own value for linear expansivity. Okay, this was gotten through experiments, all right, and has been given to us. So we have the likes of aluminium with the linear expansivity of 2.5 times 10 raised to the minus 5 per Kelvin. So it means whenever you heat up aluminium, the length of aluminium will change by 2.5 times 10 raised to the minus 5. Alright, okay, same for brass, you have it changed by 1.8 times 10 raised to the minus 5. You have iron changed by 1.2 times 10 raised to the minus 5. You have copper 1.7 down to concrete that changes by 1.2 times 10 raised to the minus 5 per Kelvin. Now let's move to the area expansion or superficial expansion. Okay, so here we hope to explore the increase in area of an object that is heated. Okay, so area expansivity of a substance is the increase in area per unit area per degree rise in temperature. Okay, so we represent area expansivity by the beta sign, and we represent the linear expansivity by the alpha sign. So whenever you see this beta sign, you know we're talking about area expansivity. Whenever you see the alpha sign, we're talking about linear expansivity. Okay, so it can be represented as this. Okay, so we have change in area all over area times change in temperature. That's increase in area per unit area per degree rise in temperature. Okay, so of course A1 represents our initial area before heat was applied, A2 final area after heat has been applied, theta 1 initial temperature before application of heat, while theta 2 is final temperature after application of heat. So we move on to the volume expansion of substances, or you can call it the cubic expansion. I will represent this by the gamma sign. So this is the increase in volume per degree rise in temperature. Okay, so we can represent that with this formula, which is increase in volume per degree rise in temperature. Okay, so we have the V1 to be initial volume of substance, we have V2 to be final volume of the substance, theta 1 initial temperature, theta 2 final temperature. Initial length, initial volume, and initial temperature are those properties before heating, while the final temperature and final volume are those properties after heat has been applied to that object. Okay, so let's also note that superficial expansivity is equal to 2 times linear expansivity, and cubic expansivity is 3 times linear expansivity. Now these are also very important formulas to note. The bimetallic strip is made up of two metals which have different thermal expansivities. Okay, so you can see here it's been drawn with two different colors to differentiate them. All right, both metals are joined together such that they can bend when temperature change. Because both metals expand at different rates, once heat is applied and expansion is happening, there's going to be a bend. All right, so that bending is used to determine the value of the temperature. Okay, we can also see that one end of the strip is fixed while the other end is left free. Okay, though both metals are welded or soldered together, the metal with the highest thermal expansivity is placed below, and the one with the lowest thermal expansivity is placed above. So once current passes through heating coils and heat is produced, the bimetallic strip begins to expand. Since the metal below expands faster, it will cause there to be a bend downwards. Okay, so you have this curving downwards, curving away from these contacts. This is easily seen in pressing irons. This is how your pressing iron cuts off when it gets to a certain temperature, okay, because you have something like this within it. Once heat is applied and that bend happens, these contacts disengage, and once they do, the flow of current is no more possible and your iron trips off. Okay, so once temperature reduces and these guys bend, it's beginning to return to normal. Okay, it comes to a point where this contact remix itself, and once it does, electricity can now flow through it, and the heater or the heating element turns back on and heating continues, and this guy begins to receive heat again and starts to expand until it bends off again and bends off this contact, and then of course electricity cuts off, and the same process continues in circles, and that's why you have your heating iron coming on and going off at intervals depending on the temperature of the iron at the time. So this is an application of expansion right here to solve a problem. Okay, you know, we're talking about applications and effects. This is an application. Okay, so let's move to the second one, which is expansion in bridges and rail line. All right, bridges made of concrete or those made of metals, they expand when temperature is high, okay, on a hot day, and contract on days we have low temperatures. Okay, so there are usually joints made of these bridges called the expansion joints, and they are made to allow for expansion and contraction naturally without cracking. Okay, so if they were not there, you could have your concrete cracking or your steel cracking due to the constant want or need to expand and contract depending on the temperature of the day, and that would yield to cracking and would damage your bridge. But due to the provision of these expansion joints, you have a freedom for them to contract or expand. Okay, usually rollers are placed under them so they can expand on that roller and contract on that roller without having to affect the structure of your bridge. Okay, so one edge of the bridge is usually fixed and the other end is usually put on rollers. Now, this expansion in bridges and rail lines is an effect heat energy has on bridges, and we try to mitigate, or we try to make sure the effect doesn't turn negative by providing solutions, all right, like the expansion joints on these bridges or rail lines. So we go to the third one, which is sagging of wires. Metal wires used in overhead cables, you know, those overhead transport cables, they usually expand also and they contract depending on temperatures. So normally when installing them, they are installed intentionally to sag, all right, so that when contraction happen, they don't snap. All right, if they snap in cold seasons, then of course there will have to be replacements that will cost so much money. Okay, coming back to replace cables that you just mounted and all that. So they are actually sagged intentionally so that there's room for contraction and room for expansion. Okay, so this is also an effect, not an application. Okay, why I'm making this distinction is because most times you encounter them in exams. The expansion in liquids. Liquids usually expand on heating and contract when cool. But since liquids most of the times are stored in a container, their expansion while in the container is not their actual or real expansion, because some parts of the thermal energy is used also to expand the container. Alright, so there comes the terms real expansivity and apparent expansivity. So real expansivity is the increase in volume per unit volume of the liquid per degree rise in temperature. The apparent expansivity is the increase in volume per unit volume of the liquid per degree rise in temperature when the liquid is heated in an expansible vessel. So the difference between the real expansivity and the apparent expansivity is the presence of an expansible vessel, right, containing the liquid. So in other words, we have that real expansivity is equal to apparent expansivity plus the expansion of the container. So in a situation where we have a container holding a certain volume of water and an increase in temperature causes it to displace some, all right, since it can't accommodate that expansion, okay, so in that situation we'll have apparent expansivity to be the volume of liquid displaced divided by the volume of liquid in a container times change in temperature. We can also use mass in place of volume since they are both proportional. Alright, so apparent expansivity can also mean mass of liquid displaced over mass of liquid in container times change in temperature. Okay, so let's move on to take a little dive into the anomalous expansion of water. First of all, I want us to go to the dictionary. What does anomaly mean? When you say this is an anomaly, what does it mean? Okay, a quick search on Google will help us to see that it is something that deviates from what is standard, what is normal, or what is expected. Okay, you have a standard or you have something that you expect or a norm, and this particular thing deviates from it. It is an anomaly. Okay, so when we talk about the anomalous expansion of water, it means there's an expectation we have for expansion, but for water, that expectation is not met. This is because water expands normally when heated and also contracts when cool, which is normal. But that happens up to 4 degrees Celsius, at which point it starts to expand. Alright, therefore it becomes less dense. So you notice that this is why water freezes from top down. Water doesn't freeze from down. If you have water in a jar and it's in the fridge, probably water doesn't freeze from down up. All right, it freezes from top to down. Okay, because the cold and the less dense layer of water always floats upward, while the more dense one goes beneath. All right, and that's why you see organisms can survive underwater on very cold days when you're in very cold regions. Okay, because you see the surface of the water gets frozen, while beneath, way down beneath, you have activity going on, because down there is not frozen, it's just cold. Because of course the water that gets less dense moves upwards, okay, and those ones that are more dense go downwards, because when water is cooled down to a certain temperature, it begins to expand. All right, which is not normal compared to other bodies or other commodities. Okay, you have them contract. Once heat energy is extracted from them, they begin to contract, and they continue to contract and remain in their contracted state until heat energy comes back. They begin to expand. But for water, contraction happens up until 4 degrees Celsius. At that point, expansion begins to happen, and that expansion makes that bulk matter become less dense and will help it to float upwards, while the more dense ones go downwards.